Hi and welcome to another chemistry lesson, and this time we're actually shifting some gears from reaction rates, which we will still use and refer to here, but now we're looking at chemical equilibrium. And so let me jump right ahead and explain what I mean by chemical equilibrium. Okay, a reaction can only be in chemical equilibrium if two things occur. It is reversible, and it is occurring in a closed system. Okay, in other words, none of the products can escape. Well, actually, let me explain both of these by using an example. A reversible reaction is a reaction that can go both ways. Let me show you an example by taking the reaction between nitrogen and hydrogen to produce ammonia, NH3. Let me just balance that. We've got two. I'll put two nitrogens here. Now I've got two nitrogens there. Now I've got 6 hydrogens in total. I only have 2 on this side, so I have to put 3 there, so that I've got 6 hydrogens. There we go. Now this is a reversible reaction, and what that means is that this is not the correct sign to use, because in synthesizing this, in other words, adding molecules together to produce a new molecule, okay, this new product this product that is formed can decompose to produce the original reactants. So in other words, I can go both ways in this. I can either go forward, okay, or this reaction can go in reverse. So these typical it's called two-way harpoons, or you can use a double arrow. It's not wrong. Okay, I like to use the two-way harpoons. Just refers to this reaction being able to go both ways. Okay, so this is called a reversible reaction. Is a reaction where the reactants can produce a product, but the product can again react to produce the original reactants. Okay, so my products can become reactants. The next thing is it can only be in equilibrium if it's a closed system. Both of these products are gases. Okay, so in other words, for them to react with one another, it needs to be in a closed system. Okay, there's a closed system. There's gas of the one and the gas of the other one. So obviously, if it's not a closed system, this is going to escape. But that's not really what it's about. The point is, this is also a gas. It doesn't just reversible reactions and chemical equilibrium doesn't just involve or don't just involve gases, but the point is that none of the products formed are taken out of the system, and the same goes for the reactants, because they again become products themselves. Okay, nothing can escape the reaction, so everything stays there where the reaction is occurring. That is what we call a closed system. Now these are the conditions that we need in order to reach chemical equilibrium. But what is chemical equilibrium? The word equilibrium, look at that part, equal, okay, the word equilibrium means that it's reached as a stable state, in a sense. Not really stable, but you'll understand in just a minute. Okay, imagine I have in my reaction I have now just added nitrogen and hydrogen together. Okay, so I've got a certain in here I've got a certain percentage of nitrogen, and I have a certain percentage of hydrogen, and I have no percentage of the product yet. Okay, so there's nothing to decompose yet. But now, as nitrogen and hydrogen is reacting with one another, it is producing a certain percentage of ammonia. Okay, so it's not zero anymore. And as ammonia is producing, it is also slowly decomposing back into that. Now that doesn't mean there's now no percentage of ammonia left, okay, because the rate at which ammonia is being produced, and this is where rate of reaction is going to come in, the rate at which ammonium is being produced is still higher than the rate at which it is decomposing. So a silly example might be that every second I'm producing 1 mole, let's say every second I'm producing 10 moles. That's a lot, okay? But I'm producing 10 moles of ammonia, okay? But every second 1 mole of ammonia is decomposing, okay? So my forward reaction rate is 10 moles per second. My reverse reaction rate is 1 mole per second. So obviously I'm increasing in the number of or the amount of ammonia that exists. But remember now what happens. As I'm producing ammonia, these quantities are decreasing because they're being used up. What does that mean? That means that their concentration in the closed system is reducing. And do you remember what happens to the reaction rate when we increase concentration? It increases the reaction rate. So the opposite is also true. As the concentration, now remember what concentration means. It means the number of particles versus the number of other particles. So for example, the number of particles of nitrogen compared to these particles are decreasing over time because we are using it up to produce that. Okay, the same with hydrogen. Okay, and this one's concentration is increasing. So this reaction rate is increasing because its concentration is increasing. So the reaction rate, this 10 mole per second, is starting to decrease. This 1 mole per second is starting to increase. So at some point they are going to stabilize. The amount of products that is formed, the rate of the forward reaction, so the rate of the forward reaction at some point will be equal to the rate of the reverse reaction. So in the example that I'm using here, the rate at which I'm producing ammonia and the rate at which ammonia is decomposing back at some point has to be equal. Okay? And that point, the point at which these two are equal, is called the equilibrium. Okay. And actually more specific, it is called dynamic equilibrium. Now there exist other types of equilibriums, many different types of equilibriums, but when we specifically talk about the rate of the forward reaction equal to the rate of the reverse reaction, it means that we have reached a state of dynamic equilibrium. Now, what that does not mean, it does not mean that the reaction stops occurring. It does not mean that all of a sudden nothing is happening anymore. What it means is that the rate at which products are produced and the rates at which the product is producing the reactants again are the same, so that there are no net changes in the percentages. So these percentages, okay, so that means no net changes in the ratios. In other words, every second this percentage and that percentage and that percentage stays the same. Yes, nitrogen is still being decomposed from from ammonia, but ammonia is also being produced from the reaction between these two, so there's no net change in these percentages. Okay. Now what it also does not mean, it does not mean that these percentages are equal to each other. Okay. It does not mean that these percentages are equal to each other either. It just means that the percentages stay the same. Now what we are going to look at in future videos is how can we increase these percentages. So for example, this process called the Haber process is the process of producing ammonia, okay, for various applications. Ammonia is a very practical product, but the problem is it decomposes. So what and so when in the industry, when they're producing ammonia, we have a problem. When we produce it, it goes back to its original reactants. So what can we do to favor this reaction so that we can produce a higher percentage of this? Okay, it has to happen in a closed system when we do this, but there's now certain things that we can do to improve this reaction to produce more products, and that's what we'll look at in the future video. What I do just still want to look at in this video is actually a mole versus time diagram. Okay, a mole versus time diagram to illustrate dynamic equilibrium visually for you. Okay, and I think what would be helpful is if you just see this in a graph form. So let's say we had ammonia here in sorry, not ammonia, we have nitrogen here in blue. Actually, let's make nitrogen lower. This is my nitrogen would be in blue, and then you'll see that in this reverse reaction we need, for every one nitrogen we need 3 hydrogens. So obviously the quantity in hydrogen would be more, so it would be here. That's where we would start that one, and then obviously in the beginning of my reaction I will have absolutely no ammonia. Okay, so I won't have any ammonia. Now as this reaction occurs, we have a lot of ammonia and a lot of hydrogen and a lot of nitrogen. So in the beginning these two can immediately start reacting with one another, but as time goes by, less of it is being used up and some of it is being produced. So usually if it's not a reverse reaction, then the limiting reagent will go way down up to the bottom as it is completely used up. But now what happens is, because as this goes by, and I wish I can draw this at the same time, okay, actually I suppose I can. Let me do this. So notice here now that as hydrogen and nitrogen is being used up, obviously they are reducing in quantity as they being used up, and then as they being used up, ammonia is being produced, and so ammonia is being produced, and then at some point it starts being when ammonia is being reduced, the ammonia decomposes into nitrogen and hydrogen again. So at some point, even though it is the reaction rate is slowing down, remember reaction rate in a mole versus time graph, we can look at the slope of the graph. We looked at that as well. The slope of the graph is reducing, but it's not going down to 0 because ammonia is producing again hydrogen and ammonia, or decomposing into hydrogen and ammonia. So as time goes by, we just see these slopes sloping down until it literally becomes vertical. Sorry, not vertical, horizontal lines. And at the moment it has reached these horizontal lines is the moment that it has reached equilibrium. So at this point here, at that point, we have reached chemical dynamic equilibrium, because from here on outwards, the reaction rates are equal. It does not mean that there is no reaction, right? It doesn't mean, even though the slope is 0 in this case, it doesn't mean that there is no reaction. It just means that there is no change in the amount of moles and nitrogen. Doesn't mean there isn't a change. What I mean is that the amount of hydrogen produced by decomposition and the amount of hydrogen used is equal, so that there's no change in the amount of hydrogen in net change in the amount of hydrogen. That works. So hopefully you understand that. The final thing I'll just show you here is now a special value that we use called the chemical equilibrium constant. Okay, the chemical equilibrium constant. Okay, now chemical equilibrium constant, Kc, is a value that is that is calculated based on the ratio. So you can see the ratio, in other words, the percentage of each of these products and reactants are now equal. And the ratio isn't equal, it's constant. So the chemical equilibrium constant initially isn't a constant, but it reaches a constant, and the how we calculate it is taking the concentration of the products divided by the concentration of the reactants. Okay, now what do I mean by the concentration of the products and the reactants? Well, it literally means if I take the percentage of products divided by the percentage of the reactants, that is what will give me the Kc value. But specifically, when we have a reaction, let me write the reaction like this. If I have a plus B, and that produces, in a reverse reaction, very important, C plus D. Now remember, we might have coefficients here. Let's use our coefficients. Lowercase a would be the coefficient of that compound A, lowercase b the coefficient of that compound B, lowercase c coefficient of compound C, and lowercase d. Now in the example we looked at with ammonia, we had H2 plus N2 produces NH3, and then these coefficients that I'm talking about was 3 here and a 2 there and a 1 here. Now at the moment I've got these coefficients, my Kc value will look at the concentration of the products. So we'll take the concentration of C times the concentration of D. This is very important, so make sure you focus at this point. Divided by the concentration of A times the concentration of B. And now these coefficients tell me how many of these factors must I include. Okay, so if there's A of these, I must actually have A of these factors, because I have B and B. So to include that A number of factors, I can just put it as an exponent, and this would be the exponent B, that would be the exponent C, and that would be the exponent D. So if I can do it for my ammonium reaction, the formula for the equilibrium constant for this reaction, sorry, it should be reverse reaction, that's very, very important. You will lose marks if you don't put that. Okay, the formula for the chemical equilibrium would be the concentration of NH3 to the power of 2 divided, because its coefficient is 2, divided by the concentration of H2 to the power of 3 times the coefficient, sorry, the concentration of N2 to the power of 1, which I don't need to write. Now, if I can work out the concentration of this, that I can work out the chemical equilibrium. So how can I get concentration? Well, again, there's different ways of looking at concentration, but basically you can look at C is equal to N over V. The volume of this container, remember these are all gases, okay, and so I take the molar quantities, which I have here on my graph. I can look at the molar quantities and read it off here on the side, and then so that would be moles divided by the volume. For all three of these, the volume would be the same because the system is closed. Okay, they're all occurring in the same volume. So this is an example of how you can calculate concentration. It's not the only way to calculate concentration, but most definitely the most common way. And now one last element of the equilibrium constant is we only do this for gases and solutions. Aqueous. We only do this for gases and aqueous solutions. So in other words, if in our reaction equation we often state the phase form by putting a gas, liquid, solid, or solution. In other words, I've dissolved it into something next to it. The only time I will actually use the concentration in the chemical equilibrium is if I'm working either with a gas or with an aqueous solution, because these are the only ones where it makes sense to actually work out a concentration. Okay, I can't have a concentration when I'm working with a pure liquid or a pure solid because the concentration is just 1. Okay, so if I put them in here, a concentration in here, it would just be a variable of 1, not a variable, a factor of 1 with whatever. So they have no use in here. So we'll only use gases and aqueous solutions. That's all I want to say. I've already stretched this video out too long. Thank you very much for watching. I hope you understand the basics of chemical equilibrium well, and I will see you in the next video.